Hello and welcome back to Fourier Transform, the video series where we talk about the theory of the Fourier series. Indeed, in today's part 14, we will talk about the case where the Fourier series converges uniformly. You already know, in general, we only have the convergence of the Fourier series with respect to the L2 norm, but for special cases, we can make the whole thing much stronger. However, you already know, before we start talking about how this actually works, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, with the link in the description, you can download additional material for the videos. Okay, then let's immediately start by considering a 2π periodic function. And there you know, the graph could look very complicated because the only thing we need is that it is square integrable. More precisely, this means it's square integrable over an interval of length 2π. And there it does not matter which interval we choose. Usually we go from -π to π, but we could also go from 0 to 2π. So there you see, we can really use the periodicity. And now we can also put one chosen order of the Fourier series into the picture, and then you know it looks like this. Of course, this is just a sketch, but it looks exactly how our approximation with the Fourier series f and f should work. And roughly speaking, the convergence with respect to the L2 norm means that this area here, weighted with a square, goes to 0 when n goes to infinity. This is all we have in the general case, and in the formula it means that f minus f n f with respect to our L2 norm goes to 0 when n goes to infinity. In particular, it means that we don't have a pointwise convergence guaranteed at all. However, obviously the picture on the left-hand side definitely suggests that we have the pointwise convergence for most points. Therefore, the question for this video here is, can we make our convergence even stronger for some special functions f? And indeed, it turns out that for piecewise C1 functions, we even have uniform convergence. And there you should know, this is even a stronger notion of convergence than our pointwise convergence. This implies that for these special functions, we can use the Fourier series to approximate the function at each point. Therefore, showing this uniform convergence is a really strong thing. But maybe before we start with the theorem, let's first discuss a suitable example. And you might already know, what we necessarily need is a continuous function, because the uniform limit of continuous functions is always a continuous function again. However, we need more than that, and as I've already mentioned, we need C1 functions. However, we don't need that globally. A piecewise C1 function is enough. What this formally means I explain soon, but I can already show it what it means in a picture. So this one here could be the graph of our function, and you immediately see it's not a C1 function. In fact, it has some points where it's not differentiable at all. However, these are only finitely many points, and if we ignore them, then we have a continuously differentiable function on the separate intervals. And let's say that this is the graph of the function from -π to +π, and that we extend it 2π periodically. However, this extension has to be a continuous function, which means that the value of this point here at π should be the same as the value at the point -π. And of course, also inside the interval, it should not make any jumps. Okay, so there we have it. This is the graph of our function f. And now on the right hand side, let's sketch our Fourier series, starting with f0 of f. As always, this is just a constant, but then we can increase our n step by step. Hence, the next one looks exactly like this. And only one step later, we are already very close to the behavior of the function f itself. However, what is still missing are the sharp corners we have in f. And we see they come in if we increase n more and more. And there I can tell you, if you want to play with it, the corresponding Python code is in the description. I always find it quite interesting to see how good this approximation is already after only a few steps. And indeed we immediately see that we have the pointwise convergence for every point. Therefore it should definitely be possible to show that in our theory. It's not so simple because we have to leave our nice Hilbert space geometry. So instead of the L2 norm, now we have to deal with the supremum norm. Hence what we need is a relation between the two norms. Therefore, let's first write down what we know about such a relation. There I should mention that the supremum norm is also often called the uniform norm simply because it describes the uniform convergence. And the common notation is the norm symbol with an infinity sign in the index. And since we deal only with 2π periodic functions, we can restrict the supremum to a bounded interval. This means we take the supremum of the absolute value of the function f of x, where x goes through an interval from -π to π. Hence the supremum norm just measures the largest value of the function f with respect to the absolute value. Indeed, please note that for a continuous function f, this supremum is definitely a maximum. So the first conclusion is that every value of f is definitely less or equal than this supremum. This is a simple but important inequality. And obviously we have the same inequality for the squares. And since the integral is also a monotonic operation, we get the same inequality for the integrals. However, now on the right hand side here, we just have a constant function, so the integral is really easy to solve. Namely, it's the length of the interval times the constant. And now you should recognize, if we bring the factor 2π to the left hand side, then we have our nice L2 norm there. So there we have it, this is our inequality for the two norms. Moreover, we can also delete the squares, so we have that the supremum norm is always bigger or equal than the L2 norm. And in this formula you also immediately see that convergence with respect to the supremum norm is stronger than the convergence with respect to the L2 norm. Therefore we really have to put in some work to show that we have this uniform convergence. But first we have to state the theorem with all the details. And as always in the theory of Fourier series, we take a 2π periodic function. And moreover, f also has to be continuous on the whole real number line. So the picture is the same as before, we can just consider any interval of length 2π. And I want to keep our nice symmetric tradition, which means we go from -π to +π. And now you know, we want to have a piecewise C1 function, so it could look like this. So it's allowed to have such non-differentiable points, but only finitely many. Hence we can always count them, so let's call them A1, A2 and so on. Moreover, I also want to include A0, which should be our -π on the left hand side. And on the other hand, the last one should be AM, so π on the right hand side should be AM plus 1. So in summary, what we assume here is that we have only finitely many points we call AI. And they should all lie inside our interval from -π to π. And most crucially, they can be chosen in such a way that the function f restricted to the subintervals is a C1 function. And obviously the subintervals can be written as aj to aj plus 1, where j goes from 0 to m. Hence, if we consider the function with that domain, then we have a continuously differentiable function. And you know the short formulation for that is just C1. Okay, there we have it. This is the whole assumption of the theorem, which means we have a continuous function, which also includes that the values at -π and π coincide, and moreover, the function should be piecewisely continuously differentiable. And then what we get is that we have uniform convergence of the Fourier series to the original function f. And as you already know, this can be written with respect to the supremum norm, so we consider f minus the Fourier series of f and then we send n to infinity. And then the claim is that the supremum norm goes to 0. Okay, so this is the nice theorem which tells us that we actually can have uniform convergence for some special functions f. And now just to make the theorem complete, let's also put in the definition of the Fourier series. It's given as an orthogonal projection in L2, where our orthonormal system ek is given by these exponential functions. Hence again, the theorem tells us that we can uniformly approach the function f by using these exponential functions. So it's a really strong result, but before we can use it in applications, we first have to prove it. And this will need some time, so I would say let's do that in the next video. So I really hope I meet you there again and have a nice day. Bye bye.